my friends. If you're studying physics, then the legendary 1935 EPR paper is required reading. It's mandatory. In this paper, Einstein, Podolsky, and Rosen express their concerns with quantum physics, and specifically, they show that quantum physics appears to contain within it a paradox, which seems to indicate that quantum physics is incomplete. That is, it's missing some ingredients. Now, later on, it'll turn out in one of the greatest plot twists of all time that that paradox is actually not a paradox because local realism isn't really as strong of a thing as people thought. But we'll get to that in a follow-up video on Bell's theorem. But for today, I wanted to explore this paper. I wanted to go through it together, word for word, equation for equation, really taking the time to digest this paper in its full glory, to really examine in careful technical detail the argument put forth in the paper, and to think about what that means. Now, the good news is that the paper is only 4 pages long. In fact, really, it's more like 3 3/4. But, that said, this is premium Einstein content. So this is like one of the more famous papers that Einstein ever wrote. And so even though it's only a few pages, it is very sophisticated, it is very technical, and so we're not going to rush our way through it, we're going to take our time, and that's okay. Now you can access this paper totally for free, and I put a link in the description below where you can download the PDF. If you have a printer, I highly recommend printing out this paper. If you print it double-sided, it's only 2 pages, easiest job a stapler's ever had, and that way you can have it with you as we go through the video. If you don't have a printer, that's okay too. In that case, I recommend pulling up the paper on another screen, just so that you have it with you to refer to as we go through the video. Alright, so I want to start off by reading the abstract of the paper. The abstract of this paper provides an overview of the logic of the argument contained within the paper. Okay, so the abstract begins with, in a complete theory, there is an element corresponding to each element of reality. So for example, in quantum physics, we have momentum. And in reality, we have momentum, right? So that's cool. But imagine if quantum physics didn't have momentum. Well, then it wouldn't be complete. And in general, you can say, well, any aspect of reality should be described by the theory in order for the theory to be complete. And here we're working within the reductionist paradigm. And so by elements of reality, here we don't mean computationally intensive emergent things like turbulence or the results of a sports game or an election, but rather we're talking about the fundamental ingredients of reality. Like what is nature made out of when you really zoom in and you really look at the pieces, and what are all the aspects of the particles and space and all that, right? So at the reductionist level, if there's anything in nature that our theory doesn't describe, well, then our theory would be incomplete. But then the question becomes, like, what even is reality? How can you say what's real? Well, they go on to say, a sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. Now, this is by no means an all-encompassing definition of reality. Not at all. And later on in the paper, they're going to acknowledge that this is just one narrow criterion of reality, which is by no means philosophically all-encompassing. But they're really onto something here, because if you think about the condition they lay out, this concept of being able to predict something with certainty without disturbing the system, let me give you an example of that. So if you consider the various energy eigenstates of the hydrogen atom, we know from quantum physics that each one of these energy eigenstates is going to have its own specific energy eigenvalue. And if we know that the electron is in one of these energy eigenstates, then we don't have to disturb the system in order to know that it has that much energy. Because for sure, if something is in an energy eigenstate, then there really is a real quantity associated with that. And that's real. And we know that it's real because if you imagine between different energy eigenstates, the amount of energy required to excite the electron, or equivalently, the amount of energy that the electron gives off as it relaxes down into a lower energy state, we can calculate what those various levels are, as I did in my Hydrogen Part 2 video. And there are very particular wavelengths corresponding to the energy differences in these energy eigenstates, and that's real, and you can observe it, and you can see it. So anyway, I just bring that up as a specific example of what Einstein and friends are getting at when they say that something is real if you can predict it with certainty without disturbing the system. That means there's actually something there. Now remember, this is a sufficient condition, but it's not necessary. So you can have something that's real that you can't predict with certainty, right? They're not saying that all that is real is that which you can predict with certainty. But no, they're just saying that if there is something that you can predict with certainty without disturbing the system, then that thing has a reality to it. Okay, so they go on to say that in quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. The most classic example here is position and momentum. If you perfectly know the position of a particle, you don't know its momentum. If you perfectly know the momentum of the particle, you don't know its position. And that's because the position and the momentum operators don't commute. And in general, in quantum physics, the uncertainty principle tells us that whenever you have non-commuting operators, you can't know both of the quantities that they correspond to at the same time. And so that immediately begs the question of, is it the case that we just don't know the reality of those two quantities? Or is it somehow the case that those two quantities can genuinely not have the same simultaneous reality? Well, we only have two options here. Option one is that the description of reality given by the wave function in quantum mechanics is not complete, or these two quantities cannot have simultaneous reality. Think about position and momentum. Quantum physics does not give us a way to know position and momentum perfectly at the same time. So therefore, either quantum physics is incomplete because it doesn't give us that information, or in actual reality, the exact values of position and momentum cannot be simultaneously real. So option one would have us believe that the uncertainty principle is a kind of epistemic flaw in the formulation of quantum physics, a shortcoming of the theory, and option two would have us believe that the uncertainty principle reflects an ontological fact about the nature of physical quantities that are described by non-commuting operators. Here, I want to make a note that this paper has two parts, and part one of the paper deals with everything we've just talked about in this paragraph of the abstract. So part one is all about setting up that dichotomy between either quantum physics is incomplete, or that's just how reality is, and observables corresponding to non-commuting operators genuinely cannot have simultaneous reality. So part one is all about establishing that dichotomy. And so here, I want to emphasize the foundational importance in this paper of these two options. Call them option one and option two. We're going to come back to these throughout the paper. And actually, I want to take some notes here. So we have two options, option one or option two. And these options are the result of the uncertainty principle. Now, I want to say something obvious. And it's so obvious, you might be thinking, Rich, why would you even say it? It's so obvious. But it'll be important later. So, if you have one of two things has to be true, either one or two, then the negation of one implies two. That is to say, if we know that either one is true or two is true, then if one is not true, it follows that two is true. Now, I'm not saying that one is not true. I'm just saying if. And this inference is known as a disjunctive syllogism, which is way too technical of a word for something so obvious. But anyway, so the concept is, if you flip a coin and it does not land heads, then it lands tails. Well, okay, so now the abstract goes on to describe part two of the paper, which is that consideration of the problem of making predictions concerning a system on the basis of measurements made on another system that had previously interacted with it leads to the result that if one is false, then two is also false. Okay, there is a lot packed into that sentence. It's like a double negative involving wave function collapse. So hold on, let's unpack this. In part two of the paper, we're going to consider a thought experiment in which we have two entangled particles. Initially, these particles are interacting, but then they're going to be separated out to two different places in space while still remaining in an entangled quantum state that we're going to call psi. then by examining the math of the wave function collapse of psi, we're going to realize that the assumption that option 1 is false means that option 2 is false. That is to say, if you assume that quantum mechanics is complete, then you conclude that those two quantities can have simultaneous reality. And that goes directly against our disjunctive syllogism, because we've already thought about it and we're like, no, if 1 is not true, then 2 has to be true. That's the only other option. But when we examine the non-local collapse of the wave function in the thought experiment of part 2 of this paper, we're going to show that if 1 is not true, then that implies that 2 is not true. And so therefore, in the case that 1 is not true, that implies that 2 is both true and not true. And that right there, my friends, that is the EPR paradox. Because how can you have something that's true and false at the same time? I mean, come on, that's absurd. And so the only way to sidestep the paradox is to say, well, I guess option 1 must be true. Because if option 1 weren't true, that would lead to a paradox. So therefore option 1 is true, so we don't have any paradox, okay? And so that's the logical structure of why Einstein and friends concluded that quantum mechanics is incomplete. The abstract ends with a statement that one is thus led to conclude that the description of physical reality, as given by a wave function, is not complete. Now, throughout this paper, one thing I want to emphasize is that it's right. There is no mathematical mistake, there is no bad logic, there's none of that. This is a solid paper. However, this paper has one Achilles heel, which is that it assumes local causality. Now, the assumption of local causality, we'll talk about in a moment exactly what that is, but that's just the idea that an object is only going to be directly affected by its immediate surroundings, as opposed to, for example, some kind of spooky action at a distance, or like long-distance instant teleportation kind of stuff, right? So local causality is a feature of all known classical laws of physics. So to even call it an assumption, I mean, you would think certainly local causality has to be true. Based on everything that's known about classical physics and relativity, local causality, also known as locality or local realism, is like a fundamental part of how we think about the nature of reality. And so how could it possibly not be true? Well, we'll get to that in the future when we talk about Bell's theorem. But for now, just think about the EPR paradox and this paper as being like that moment where you're in a dream and you don't know that you're dreaming, but then you notice that there's like something wrong. Like there's some detail where you notice like, hey, wait a minute, that's not right. And you get that kind of tingling sensation and like the whole world around you starts to kind of crumble away. Yeah, that's the EPR paradox. It's the realization that something's not right. So today we're not going to fully wake up from the dream of local realism. We're just going to recognize that there is a dream from which we can and must eventually wake up. Now, before we get into part 1 of the paper, I want to say a few words about the principle of local causality, also known as locality or local realism, because it's such an important concept for the story of the EPR paradox. So, local causality is the idea that objects are directly influenced only by their immediate surroundings. So the classic example is if you're playing pool, a ball is only going to move once it's been hit right up close by another ball. So the proximate cause of the ball's motion is the local impact between one ball and another. But locality also applies not just to objects, but to fields. So for example, if you think about radio waves, magnetic fields, even the gravitational field, in all of these cases, even though these fields often give the appearance of some kind of action at a distance, in actuality, if you examine the dynamics of these fields, like for example Maxwell's equations or the Einstein field equations, you see that the dynamics of these fields are indeed local phenomena where a ripple in the field cannot travel instantaneously, but can travel at most the speed of light. And any object at some position x is going to interact with the field based on the value of the field and/or its derivatives at that point x. The way to really see this is just imagine you're floating on a lake, and a boat goes by, and eventually the wake from the boat is going to make you bob up and down. but the wake has to get to you first. And so the boat never directly affects you at a distance, it just creates something that travels to you and then affects you locally. And then you might think, well, I can hear the boat at a distance. Yeah, but those are sound waves. And so fundamentally it's the same thing. It's the sound waves then have to get to your eardrum before they affect you. So even when you hear the boat at a distance, you're not really hearing it at a distance. You're hearing the wake that it created in the sound waves in the air when those sound waves get right up next to your eardrum. Then you might think, well, I can see the boat at a distance, so surely the boat is affecting my eyes at a distance. But again, it's like, no. What you're seeing when you look at the boat are the waves in the electromagnetic field that reflected off of the boat and are hitting your eye. But those waves also have to propagate through the electromagnetic field before they locally affect your eye. And when you meditate on all that, you realize, oh, everything is waves. And my friends, I regret to inform you that the hippies are right about that, okay? But yeah, so anyway, that gives you a sense of what we mean by local causality. So something that would violate local causality is like, imagine if you had a radio tower sending a song to a radio somehow instantaneously, like faster than the speed of light. Well, then you'd have to say, hey, what's going on here? Where's the chain of cause and effect? Because a chain of cause and effect can only ripple at most the speed of light, which is also the speed of gravitational waves. It's just the speed of a massless thing. And so anyway, Einstein strongly believed in local causality and thought that it would be unreasonable not to. And honestly, you can totally understand where he's coming from. Even nowadays, when we know that quantum mechanics can apparently kind of violate local causality, it's still something that is difficult to contend with and to really digest. Now, unfortunately, the non-local phenomena of quantum mechanics cannot be used for faster-than-light communication. You can look up the no-signaling theorem for an explanation as to why that is. I'm not going to get into that in this video today. Okay, now there's one more idea that I wanted to explore before we get into part 1 of the paper, as a bit of a mathematical warm-up and something that'll put us in the right state of mind for thinking about the ideas explored in this paper. So I want to look at the fact that the position and momentum operators do not commute. That is to say, x hat p hat is not equal to p hat x hat. And to show that these operators do not commute, we can calculate the commutator of x hat and p hat, which is simply defined as x hat p hat minus p hat x hat, where x hat is simply x, meaning that if you apply the position operator x hat to our wavefunction psi, that's simply the same thing as multiplying x by psi, and then p hat is negative IH bar times the partial derivative with respect to x, meaning that if you apply the momentum operator p hat to psi, you end up with negative IH bar partial psi partial x. We've gone into this concept in my other videos, for example, hydrogen part 1, and this is just sort of introductory quantum physics, and you can also find this in the quantum physics textbook. Now, to evaluate the commutator of x hat and p hat, you want to think about that as applying these two operators to the same wave function, but in different orders, and then subtracting the results to see what is the difference if we first apply p hat and then x hat, versus first applying x hat and then p hat. And if that difference is non-zero, then the order that we apply these operators matters, and therefore these operators do not commute. And then, as we'll talk about, that has implications for the uncertainty principle. Okay, so first, let's see what happens if we consider the expression x hat p hat acting on psi. So the way to think about that is we're actually first applying p hat to psi, then we're applying x hat to that. So we get the expression negative IH bar x hat partial psi partial x, where you see we've first applied the momentum operator to psi, and then we've multiplied that on the left by x in accordance with the x hat operator. Now here I've gone ahead and scooted over the constant negative IH bar to the outside of that expression, just to make it look a little prettier. Okay, so that's pretty straightforward. But now if we take the expression p hat acting on x hat acting on psi, then we have negative IH bar partial derivative with respect to x of x hat acting on psi, which is x times psi, and then we'll have to use the product rule to evaluate that derivative. So we take the derivative of x times psi. First we get x times the derivative of psi, and then we get psi times the derivative of x. And the derivative of x with respect to x is simply the number 1. All right, so then let's smush these two expressions together and say what would happen if we had x hat p hat minus p hat x hat acting on psi, well, we just take that first expression, negative I h bar x partial psi partial x, and then we subtract the second expression, which starts with a negative sign, so that becomes a positive sign, and then we have I h bar times x partial psi partial x plus psi. Now then you see that the negative I h bar x partial psi partial x cancels out with the other derivative term, so those go away, and then we end up with I h bar times psi. So by looking at that, we can see that if we apply this commutator expression to psi, we get I h bar times psi, and so then we see that the commutator of the position and momentum operators is I times h bar, which is not zero. So all that's to say, the position and momentum operators do not commute. Now I know this is kind of an esoteric point, and you might be wondering how does that fit into the ideas we're talking about today? Well, in quantum mechanics, the uncertainty principle says that the product of the uncertainty between two observables A and B is always going to be greater than or equal to 1/2 of the absolute value of the expectation value of the commutators of the operators corresponding to A and B. And I'm not going to prove that today, we'll just take that as a given. But then if we take that principle and apply it to position and momentum, we find that the product of the uncertainty of position and momentum always has to be greater than or equal to h bar over 2. Because if you put I h bar into the commutator expression in that principle, you end up finding that 1/2 of its absolute value is going to be h bar over 2. Now that's a very small number, because Planck's constant is a very small number. And so in everyday life, macroscopically, h bar over 2 is essentially 0. That's why you can play baseball and you can throw a ball and you can look at it and you can see where it is and how fast it's going, and we don't have an intuition for the uncertainty principle because h bar is such a tiny number relative to the things that we interact with. But in the quantum world, where you're dealing with small things and now h bar matters, then the uncertainty principle definitely becomes relevant. Not only experimentally, but also philosophically. What does it mean that the product of the uncertainty of the position and the uncertainty of the momentum of a particle is always greater than or equal to some small but non-zero number? Does it mean that quantum mechanics simply can't tell us both the position and momentum of a particle at the same time? Or does it mean that the position and momentum of a particle can't be simultaneously precisely real at the same time? Like, what's going on there? That's super weird, right? The conventional view, by the way, is that it's a statement about the blurriness of reality. But we'll talk about that as we get into the paper. And speaking of, I think now would be a great time to start reading part 1 of the paper. Part 1 begins with, any serious consideration of a physical theory must take into account the distinction between the objective reality, which is independent of any theory, and the physical concepts with which the theory operates. That is, one must always be mindful that the map is not the territory. These concepts are intended to correspond with the objective reality, and by means of these concepts, we picture this reality to ourselves. In other words, of course, our concepts are not the thing in and of itself, but it's the best we can do. We have to try to describe the world somehow. You know, it's like that story of the Zen master holding up a stick and asking his student, "What is this?" And the student says, "Oh, that's a stick." And then the Zen master hits the student with the stick, gently. And the lesson of that is that there's the world and there's language. There's the thing in and of itself, and then there's the linguistic scaffolding we put around it in order to try to make sense of it. But then, how do we know that our words or equations or whatever symbols we're using, how do we know they're any good? How do we know our language games are going to be successful? Well, in attempting to judge the success of a physical theory, we may ask ourselves 2 questions. 1, is the theory correct? That is to say, if we do some calculations with our theory, do the calculations actually match the experiment? Well, if so, then that's correct. If the numbers are wrong, that's not correct. And 2, is the description given by the theory complete? Which is to say, does the theory have any blind spots? Or does it account for all the things that it should be accounting for? It is only in the case in which positive answers may be given to both of these questions that the concepts of the theory may be said to be satisfactory. So we want a theory that's correct and complete. The correctness of the theory is judged by the degree of agreement between the conclusions of the theory and human experience. This experience, which alone enables us to make inferences about reality, in physics takes the form of experiment and measurement. Not because that's some all-encompassing way of experiencing reality, but simply because the empirical mode of interacting with nature gives us repeatable and consistent clues about what's happening in the world. And so famously, physics is kind of limited in scope, in that, it's not poetry, but it is very powerful and it is very solid. One, of course, should indulge in art and music and poetry and all of that, but physics is a fantastic philosophical scaffolding. And just so you know, in 1935, quantum physics did appear to be correct. So Einstein, Podolsky, and Rosen weren't questioning the correctness of quantum physics, but rather, their claim was that quantum physics was incomplete, that it was missing something. And so they say, it is the second question that we wish to consider here as applied to quantum mechanics. So this paper will be focused on the completeness or lack thereof of quantum physics. But what exactly does it mean for a theory to be complete? Well, whatever the meaning assigned to the term complete, the following requirement for a complete theory seems to be a necessary one. Every element of the physical reality must have a counterpart in the physical theory. We shall call this the condition of completeness. The second question is thus easily answered as soon as we are able to decide what are the elements of physical reality. And just as a reminder, that second question is the description given by the theory complete? So as soon as we can define what are the elements of physical reality, we can easily answer the question of whether our theory is complete just by thinking about, does it include all of the ingredients of physical reality, or is it missing something? And so now then, we have to define what do we mean by elements of physical reality. Well, the elements of physical reality cannot be determined by a priori philosophical considerations, but must be found by an appeal to the results of experiments and measurements. So that's the physics attitude. That which is real is that which we can observe and measure in experiments. But that's not to say that experiments and measurements give us a comprehensive definition of reality. A comprehensive definition of reality is, however, unnecessary for our purpose. We shall be satisfied with the following criterion, which we regard as reasonable. If, without in any way disturbing a system, we can predict with certainty, i.e. with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Like we talked about earlier, imagine hydrogen in an energy eigenstate. You know that it has a certain energy, and so therefore there's a certain reality to that energy. And so predictability implies reality, though you don't want to get that backwards. That's not to say that reality implies predictability, okay? Remember, this condition is sufficient but not necessary. It seems to us that this criterion, while far from exhausting all possible ways of recognizing a physical reality, at least provides us with one such way, whenever the conditions set down in it occur. Regarded not as a necessary, but merely as a sufficient condition of reality, this criterion is in agreement with classical as well as quantum mechanical ideas of reality. Okay, so on that topic of being able to predict a quantity with certainty, the paper goes on to define an eigenfunction. To illustrate the ideas involved, let us consider the quantum mechanical description of the behavior of a particle having a single degree of freedom. So in other words, we're going to consider one spatial dimension, call it x. And the reason we're considering a one-dimensional analysis here is just because we don't have to get y and z involved. I mean, come on, that's just going to make a mess, right? So everything we're talking about in this paper If you want to, you can rederive this whole argument in a fully three-dimensional context with x, y, and z, and a really messy wave function. But the point is, we don't have to. Well, okay, but how do we describe a quantum particle with a single degree of freedom? Well, the fundamental concept of the theory is the concept of state, which is supposed to be completely characterized by the wave function psi, which is a function of the variables chosen to describe the particle's behavior. So we can imagine psi as a function of x. And in quantum physics, there's a lot of conceptual machinery that's built on top of psi. Most famously, the probability density of the particle is proportional to the magnitude of psi squared. And likewise, we can get other information from the particle, like its momentum or position or energy, by applying various operators to the wave function. So the wave function in quantum physics allegedly encodes all of the information there is to know about this particle. And I say allegedly because Einstein, Podolsky, and Rosen are saying, well, hold on now, actually the wave function is missing something, and quantum mechanics is incomplete, or so they claim. Anyway, in accordance with the machinery of quantum physics, corresponding to each physically observable quantity A, there exists an operator which may be designated by the same letter. Nowadays, it's fashionable to put a hat on your operator. So if we're talking about the observable quantity A, we'll write A hat as the operator corresponding to A. So now, if psi is an eigenfunction of the operator A hat, that is, if we define psi prime as the operator A hat acting on psi, and if that equals A times psi, where A is a number, then the physical quantity A has with certainty the value A whenever the particle is in the state given by psi. So let me just pause here and reflect on this for a moment. The operator corresponding to an observable is generally going to be something involving derivatives or multiplying by a coordinate or transforming our wave function in some way. And if we pick an arbitrary wave function psi, then apply that operator to it, usually it's going to mess up psi in a kind of complicated way, and so the transformed psi prime is generally going to be pretty unrecognizable relative to the original psi. But when psi is in a state such that the operator acting on psi simply gives you a scaled version of the original psi, then we say that is an eigenstate or an eigenfunction of that operator. And in accordance with the rules of quantum physics, when psi is an eigenfunction of an operator corresponding to some observable A, then it for sure has a particular value of A, and that value is that scale factor. You apply the operator A hat to psi, you end up with some constant scale factor A times psi. That scale factor is the magnitude of the observable quantity A, for sure, with no variance on that. There's no uncertainty for an eigenstate. So a momentum eigenstate has a precisely known momentum, an energy eigenstate has a precisely known energy, and so on and so on. So now then, in accordance with our criterion of reality, for a particle in the state given by psi, for which equation 1 holds, that is to say, for an eigenstate, there is an element of physical reality corresponding to the physical quantity A. And that's exactly what I was saying earlier about the hydrogen energy eigenstates having real energy. Well, now here we've just generalized that to any quantum state. Anytime psi is an eigenstate of some operator corresponding to some observable A, then there really is a real quantity A corresponding to that particle. So all we've done here is we've generalized this thing about the hydrogen energy eigenstates. The paper goes on to give an example of an eigenfunction, in particular, a one-dimensional momentum eigenstate. Let, for example, psi equal e to the I p naught x over h bar, where h bar is Planck's constant divided by 2 pi, p naught is some constant number, and x is the independent variable, in other words, the coordinate of the particle. Since the operator corresponding to the momentum of the particle is p hat equals negative I h bar times the partial derivative with respect to x, and by the way, in the paper they do a 1 over I, but 1 over I is the same as negative I. Well, anyway, so if we apply our momentum operator to our wave function psi, we see that the transformed psi prime, is equal to p hat acting on psi. In other words, we have negative I h bar times the partial derivative of psi with respect to x, and because psi is an exponential, when you take its derivative with respect to x, you end up popping out a factor of I p naught over h bar, and then the I over h bar cancels out with the negative I h bar, and you end up with the p naught times the exponential. In other words, you end up with p naught times psi. And p naught is a constant number. So we see here then that p hat acting on psi is some constant number p naught times psi. That is to say, psi is a momentum eigenstate. Thus, in the state given by equation 2, the momentum has certainly the value p naught. It thus has meaning to say that the momentum of the particle in the state given by equation 2 is real. Right? So if a particle is in a momentum eigenstate, it has a real momentum. Because if you know that psi is in a momentum eigenstate, then you can say with certainty that it has a particular momentum without having to mess around with that wave function. But in quantum physics, if you know the momentum perfectly, then you know nothing about the position. The paper goes on to show that. So you see, a momentum eigenstate is not a position eigenstate. Because, on the other hand, if equation 1, which is the definition of an eigenfunction, a hat operating on psi equals a times psi, does not hold, we can no longer speak of the physical quantity a having a particular value. That is to say, in general, if our wave function psi is not an eigenstate of the operator corresponding to the observable a, then we do not know with certainty the quantity of that observable for that particle. This is the case, for example, with the coordinate, that is to say, the position, of the particle. The operator corresponding to it, say q hat, is the operator of multiplication by the independent variable. Thus, q hat operating on psi equals x times psi, which does not equal a times psi. Okay, so what have we done here? Well, q hat is the position operator. It's a very simple operator. In quantum mechanics, all we do for the position operator is we just do x times psi. But remember, x is this variable, and so x times psi is not going to be a constant times psi in general, right? Because x changes from one place to another, and if a is supposed to be constant, then for some arbitrary wave function psi, it's not going to be true that x times psi is equal to a psi. Especially if our wave function psi is a momentum eigenstate. In fact, a momentum eigenstate, because it has a precisely known momentum, is going to have a totally unknown position. So let's go ahead and prove that. So in accordance with quantum mechanics, we can only say that the relative probability that a measurement of the coordinate will give a result lying between a and b on the x-axis is the integral from a to b of psi star psi dx. Now, psi star is the complex conjugate, and so psi star psi, just think of that as the magnitude squared of psi, which remember, magnitude squared of psi, that's the probability density. So we're integrating over the x-axis from some interval a to b of the probability density of the particle times dx. But then for a momentum eigenstate, we have an e to the I something, and the magnitude of e to the I something is always 1 because its phase changes but its magnitude doesn't. So then we end up simply with the integral from a to b dx, which is just b minus a. In other words, the relative probability of finding the particle between some interval a and b on the x-axis, if it's a momentum eigenstate, is just the width of that interval. Okay, so since this probability is independent of a, but only depends on the difference b minus a, we see that all values of the coordinate, that is the position, are equally probable. So there's no specific location A on the x-axis where the particle is more likely to be. When it's in a momentum eigenstate, its position is entirely spread out uniformly across all of x. So what does that tell us? Well, if momentum is known, then position is not. A definite value of the coordinate, that is the position, for a particle in the state given by equation 2 the momentum eigenstate, psi equals e to the I p naught x over h bar, is thus not predictable, but may be obtained only by a direct measurement. So if you have a momentum eigenstate, you want to know its position, you'd have to measure the position. But such a measurement, however, disturbs the particle, and thus alters its state. After the coordinate is determined, the particle will no longer be in the state given by the equation 2. So you measure its position, and now it's no longer in a momentum eigenstate. But so then what's its momentum? See, and now you know the position, but now you don't know the momentum. The usual conclusion from this in quantum mechanics is that when the momentum of a particle is known, its coordinate has no physical reality. That's the usual conclusion, is that quantum physics is complete, the wave function tells us everything we need to know, and so if the wave function math is such that you know the momentum, you don't know the position, well, then if the momentum of the particle is known, then there's no reality to its position. That's kind of the standard orthodoxy. And that's what Einstein, Podolsky, and Rosen are challenging in this paper. So let's generalize this. Instead of just position and momentum, let's talk about A and B, where A and B are two physical quantities whose operators don't commute. More generally, it is shown in quantum mechanics that if the operators corresponding to two physical quantities, say A and B, do not commute, that is, if A hat B hat does not equal B hat A hat, then the precise knowledge of one of them precludes such a knowledge of the other. Right, so that's the uncertainty principle. Furthermore, any attempt to determine the latter experimentally will alter the state of the system in such a way as to destroy the knowledge of the first. So you have a momentum eigenstate, you measure its position, well now it's no longer a momentum eigenstate. So you get momentum or position, but not both. You get A or you get B, or you get some uncertain combination thereof, but you don't get precise numbers for both at the same time. And in quantum mechanics, you can't. The math does not allow you to do that. From this, it follows that either, 1, the quantum mechanical description of reality given by the wave function is not complete, or 2, when the operators corresponding to two physical quantities do not commute, the two quantities cannot have simultaneous reality. So that's that dichotomy we were talking about earlier in the abstract. For if both of them had simultaneous reality, and thus definite values, these values would enter into the complete description, according to the criterion of completeness. If the particle had a real position and a real momentum, then a complete theory should be able to tell us both of them at the same time. And so if then the wave function provided such a complete description of reality, it would contain these values. These would then be predictable. But that's not how it is in quantum mechanics. This not being the case, we are left with the alternatives stated. All that's to say, we have two options, option 1 or option 2, and these come from the uncertainty principle. Okay, but then, is quantum mechanics not complete? Well, in quantum mechanics, it is usually assumed that the wave function does contain a complete description of the physical reality of the system in the state to which it corresponds. That is to say, the negation of option 1. At first sight, this assumption, the negation of 1, is entirely reasonable, for the information obtainable from a wave function seems to correspond exactly to what can be measured without altering the state of the system. That is, quantum mechanics appears to work, so why shouldn't we trust it? Well, we shall show, by analyzing an entangled two-particle state, however, that this assumption, the negation of 1, together with the criterion of reality given above, leads to a contradiction. That contradiction being the EPR paradox, where, as we laid out in the abstract of the paper, the non-local collapse of psi is going to tell us that the negation of option 1 implies the negation of option 2, so then option 2 is true and false at the same time. That's a paradox, we can't have that, and therefore it follows that option 1 is true and quantum mechanics is incomplete. That's the argument, at least. And it's a strong argument. If not for its dependence on local causality, it would be totally true. All right, my friends, part 2 of this paper is going to be quite mathematically sophisticated. And so before we get into it, I want to say a few words about some of the concepts that we're going to be talking about in part 2 of the paper. And I hope that by going through these mathematical concepts before reading part 2, then when we finally get to reading part 2, we're not going to get hung up on the equations, but instead we'll be able to focus on the ideas and the philosophy because we'll already be familiar with the math. All right, so the first mathematical concept I want to talk about is the Dirac delta function, also known as delta of x. The Dirac delta function is defined as a Gaussian distribution, that is a bell curve, which has been squeezed so tight that it becomes a perfect spike with infinitesimal standard deviation sigma. So to write that mathematically, we would say that the delta function of x is the limit as the standard deviation, which is a positive number, approaches 0, of a properly normalized Gaussian distribution, which has the form 1 over the square root of 2 pi, sigma, e to the negative x squared over 2 sigma squared. And that orange expression there, that is simply the definition of a Gaussian distribution, which has an area under the curve of 1. So e to the negative x squared over 2 sigma squared, that gives you that distribution along the x-axis, that lumpy pattern, and then the coefficient in front of that, the 1 over square root of 2 pi, sigma, that is going to properly adjust the height of the curve so that the area remains 1 for all possible values of sigma. So in the animation shown here, I'm sweeping through the values of sigma, and you'll notice that all of these bell curves have the same area. It's only the standard deviation that's changing. So you see how we're sweeping out that family of functions, and the Dirac delta function is simply the limit in all that family of functions as sigma approaches 0. So the delta function can be a little confusing, because if you think about it, it's like, okay, so delta of x is going to be infinity if x equals 0, or it's going to be 0 if x is not equal to 0. And yet the integral over the delta function dx is equal to 1. So we have here, at one location which is infinitesimally thin, it's also infinitely tall. And the infinity times the infinitesimal, by definition, equals 1. Now, of course, you can imagine that the definition of such a concept has to be taken very carefully and with nuance and subtlety. And so a mathematician might tell you that technically the Dirac delta function is not really a function. It's a distribution. It's kind of a generalization of the concept of a function. It's the limit of a function as a certain parameter approaches 0. But anyway, let me tell you how we think about a Dirac delta function in physics. We think about it as we have a Gaussian that is so tight that its width doesn't matter. And that's really all there is to it. So in physics, this thing about infinities and infinitesimal, you really don't have to take that too literally. And even though in practice, reality is never perfectly sharp, but we use the delta function in arguments where some small blurriness is irrelevant. So that's all it is. And so whenever someone uses a delta function in an argument, you never want to say, hey, that argument is flawed because you're invoking this thing that's infinitesimal and infinite and all that. No, because you can always replace the delta function with a very tight Gaussian, if you'd like. But then usually you would just be making the argument more mathematically complicated without really changing the philosophical essence of what's being said. So we're going to use delta functions in part 2 of this paper, and they're invoked in that context, where the EPR paradox does not depend in any way on the perfect sharpness of the delta function. Okay, now there's an important property of the delta function which we're going to use in part 2 of the paper, and that is known as the sifting property. So the sifting property is the idea that if you have the integral over x of delta of x minus a times some function f of x, then that equals f of a. Now this equation looks a little fancy, but actually the idea is not so complicated at all. Because remember that delta of x minus a is going to be 0 everywhere, except where x equals a, because at that point you have a minus a, which is 0, and delta of 0 is infinite. So then you see that we can break up our integral into 3 parts. First, we have the integral from negative infinity up to a of 0 times f of x dx. So that's going to be nothing because it's been turned off by the delta function. And then we have the integral from a to a of infinity f of x dx, Now that's kind of weird. And here I'm being a little casual in how I write this, okay? A mathematician might say, hey, you put in a limit there or something, right? But you get what I mean. And then the third part of the integral is going to be from a to infinity of 0 times f of x dx. And so the first and third parts of the integral, those are going to completely go away because the delta function there is 0. And then now all we have to contend with is this weird integral of an infinite point times a f of x over this infinitesimal interval from a to a. And it's like, okay, how can we make sense of this? Well, for starters, we know that this integral cannot depend on the function f evaluated at anywhere other than a, because in this integral, x can only take on the value of a. And then the reason that the result of the integral is simply f of a, as opposed to, say, 2f of a or some other factor of f of a, is because the delta function, by definition, is normalized such that its integral equals 1. And so its weight, so to speak, is simply 1. It's not going to grow or shrink the result. And so whenever you integrate over delta, that's always going to contribute a nice clean factor of 1 to the equation. So just by thinking about this in terms of infinity and infinitesimals, we got the right answer. But notice that if you wanted to be more formal, and if you wanted to replace the delta function in the integral with a very tight Gaussian centered at x equals a, then the result you get from that method is going to be very close to f of a. And then in the limit that the standard deviation approaches 0, the result is going to converge precisely to f of a. And so you see how the infinity in the delta function is just an intermediate concept which washes away and yields a sensible result. Okay, so if that makes sense, then you have a good understanding of the delta function, and that's really all you need to know about it. It's kind of a weird function, but it's not super weird. All right, so now the next mathematical thing that I want to talk about that's going to prepare us for part 2 of the paper is the concept of expanding a wave function psi as a superposition of discrete eigenstates u sub n with expansion coefficients a sub n for some observable quantity a. That is to say, if we have a wave function psi of x, we can write it as a sum over eigenstates u sub n of x times expansion coefficients a sub n. The reason we're able to do that is because the eigenstates of an observable comprise a complete orthonormal set. And that's sort of one of the main rules that you learn when you learn quantum physics, is that if you have an observable quantity, and that's going to have a set of eigenstates corresponding to the set of eigenvalues that are the measurable quantities for that observable, then those eigenstates give you a set of basis functions with which you can construct a more arbitrary wave function psi by superimposing a bunch of those different eigenstates. And here, by orthonormal, what I mean is that if you take two different eigenstates and take their inner product, you get 0. So they're sort of perpendicular in that sense. They don't get in each other's way. But they're also normalized. So if you take the inner product of any eigenstate with itself, you get the number 1, corresponding to a normalized wave function. We can write those two conditions in one equation by showing the integral form of the inner product between two eigenstates, and showing that that equals delta sub nm, where here this is the Kronecker delta, which takes on a value of 1 when n equals m, and takes on a value of 0 when n does not equal m. Alright, so now if you consider everything we've just talked about, and think about the fact that there are multiple observables that we can have for a given particle. Momentum, position, energy. And so we can expand psi over the eigenstates of an observable quantity in multiple different ways, corresponding to multiple different choices of the observable quantity. So the equation shown here, say this is for some observable A. Well, if instead we consider another observable B, then we could also expand psi over the eigenstates column V sub n corresponding to the observable B. And in that case, we would of course have a different set of expansion coefficients for the same psi, so call those B sub n. And so the equation shown here, it's the same equation, but just two different versions of it, where, for example, we can say that A is momentum and B is position, then a general wave function psi can be written as a sum over momentum eigenstates, or equivalently, it could also be written as a sum over position eigenstates. Let me give you a visual example of the idea of writing a general wave function as a superposition of eigenstates. We'll use as an example the one-dimensional quantum harmonic oscillator. Today I'm not going to solve the quantum harmonic oscillator, although I do have a video on that. It's one of my first videos, so the production quality isn't great, but I do show the derivation of that. In any case, the quantum harmonic oscillator is something like the quantum version of a mass on a spring, and it has energy eigenstates of the form shown here, with these various constants pertaining to the parameters of the system, and it has a discrete set of energy levels, E sub n, which equals h bar times omega times the quantity n plus 1/2. Now, if you haven't heard about the quantum harmonic oscillator yet, don't worry about it. I don't want to get into the details of it today. The only point that I want to make is that we have a system which has a discrete set of energy eigenstates. So these are states with definite energy, and as a result, the probability density remains constant in time. Sort of like a momentum eigenstate has a constant probability density in space, an energy eigenstate has a constant probability density in time, because energy is to time as momentum is to space. So anyway, what I'm showing here is the lowest energy state, corresponding to n equals 0, and you can see that the function is just kind of swinging around. And this is a very specific quantum state. It's an energy eigenstate, it has precisely known energy, and its probability density is totally stationary in time. But notice that the complex phase of the wave function is going to swing around in accordance with that time evolution factor e to the negative I over h bar e sub n times t. So these energy eigenstates have a stationary probability density, but the wave function itself is going to swing around and sort of vibe around in the complex plane at a rate that's proportional to the energy eigenvalue. Okay, so here we've seen a few examples of energy eigenstates. Now what I want to show you is that a more general wave function, which does not have a precisely known energy, can be written as a sum over the energy eigenstates, u sub n, with a set of expansion coefficients, a sub n. So what I'm showing here is a more generic wave function that's a sum over these energy eigenstates. And you see how it's kind of sloshing around? But at the same time, this generic wave function is a solution to the one-dimensional quantum harmonic oscillator. It's just not in an energy eigenstate. It's a more generic kind of a wave function. And what I'm intending to illustrate with this example is that, in general, when you have a wave function, it's kind of sloshing around and it's sort of a generic thing, you can always expand it over a set of eigenstates, in this case, energy eigenstates. And that's just a superposition of all those eigenstates, each one times an expansion coefficient. And by the way, to calculate those expansion coefficients, you can take the inner product of the eigenstate with the wave function itself. And in order for this to be properly normalized, the sum over all the amplitude squared of the expansion coefficients should equal 1, so that the wave function is neither too big nor too small, but has a probability of 1 that the particle is somewhere. Okay, so I don't want to get too much into the weeds of this particular quantum harmonic oscillator example. I only bring this up to illustrate the principle that a generic wave function psi can be written as an expansion over the eigenstates of an observable quantity. So next, I'd like to look at the concept of a two-particle wave function that describes two entangled particles. So imagine that we have two particles, which we'll creatively call particle 1 and particle 2, and imagine that they're somehow interacting. So from t equals 0 to some time t equals t, they're intermingling, and their quantum state is getting all entangled. Well then at some time, capital T, suppose these two particles go flying apart, separating in space, but still remaining in an entangled quantum state. Then suppose that these separated particles have gone on either side of an impassable barrier, so that no communication or any kind of cause and effect can travel between particle 1 and particle 2. Now you can always say, well, is it possible to have an impassable barrier? Maybe there's some kind of subtle communication that can happen even through a thick thing of lead, right? So for the sake of argument, we can even imagine that particle 1 and particle 2 end up in different light cones, so that they're separated so far out in space relative to the amount of time that we're doing this experiment that no cause and effect, even something traveling at the speed of light, could go from particle 1 to particle 2 throughout the course of the experiment. So all that's to say, we start off with two interacting particles, they separate out, and then they become completely isolated from one another while still remaining in an entangled quantum state. So that's the thing we want to imagine. And by the way, this experiment can actually be done in real life, and there's a variety of different ways to do it. For example, you can look into spontaneous parametric down conversion. That's something where you end up with a couple of entangled photons. And you can also do this experiment where you have two particles whose spins are entangled. So there's all kinds of different ways of having two entangled particles separated while still remaining in an entangled quantum state. Now, for the purpose of the EPR paper, we want an example of a two-particle wave function that is going to be very mathematically elegant and clean and easy to work with, because we're going to be making a point about the structure of quantum mechanics itself, and so there's no reason to have an unnecessarily messy wave function, even though such a wave function might correspond more closely to actual experiments, which are kind of messy. But no, it's okay for the sake of argument to use a wave function with very nice mathematical properties, just as a theoretical example to use to probe the structure of quantum physics. Everything we're about to say regarding this wave function and the collapse of the wave function, the same applies to a more realistic, more messy, more complicated wave function. But we don't need to make this derivation needlessly complicated. Okay, so the wave function that EPR uses is shown here. Psi of x1 and x2 is the integral over momentum of e to the I over h bar p x1 minus x2 plus x naught. So I think it's a good idea now to take a moment to talk about what a two-particle wave function is, and what's the deal with this one in particular. Why are we using this? What does it mean? And all that sort of thing. Okay, if we want to think about a two-particle wave function, first, think about a one-particle wave function, and think about how the probability of finding the particle at some position x is going to be proportional to the absolute value squared of psi of x. And so, famously, that's how the wave function encodes the probability density of the particle. And for the sake of argument, again, we're just thinking in terms of one spatial dimension, so as not to overcomplicate our analysis. And then if you wanted to ask what is the probability of finding that particle on some interval of the x-axis, call it capital R, then to do that, you simply integrate over that region of psi squared. All right then, well, a two-particle wave function is very similar in spirit to a one-particle wave function, but now we have something of the form psi of x1 and x2. Now think of this as a function that encodes the probability of finding particle 1 at position x1 and particle 2 at position x2. Now there's a subtlety here, which is that psi of x1 and x2, this is not like a psi of x and y. Right, so we're not dealing with like a two-dimensional spatial domain, like a plane. No, we're still talking about the one degree of freedom in space. But x1 corresponds to the position of particle 1 on that axis, and x2 corresponds to the position of particle 2 on that axis. So psi of x1 and x2, it still kind of lives on the x-axis, but in a way where now you have two particles there and you have to be mindful of both of their positions, and psi is defined as a function of both of those positions. See what I mean? And so therefore, if you want to say what is the probability that particle 1 is going to be on some interval, call it r1 of the x-axis, and particle 2 is going to be on some interval, call it r2 of the x-axis, well then we would integrate over both r1 and r2 of psi of x1 and x2 squared. And so in that way, the two-particle wave function encodes the probability density of both particle 1 and particle 2, but in a way where it's all kind of entangled. You know, these things, particles 1 and particle 2, they're related in this wave function. Because depending on the nature of our two-particle wave function, there can be non-trivial relationships between how psi depends on x1 and x2. Right, this function kind of entangles the two particles together. as we'll see when we explore the properties of the psi that's used in the EPR paper. So speaking of, Einstein, Podolsky, and Rosen make a very sharp argument using an idealized state, psi of x1 and x2, where the two particles have perfectly anti-correlated momentum. That is to say, the momentum of particle 2 is for sure equal and opposite to the momentum of particle 1. But the wave function does not tell us what that momentum value is. That's something that would have to be measured. So we'd have to collapse the wave function in order to get a number for that momentum. And likewise, the EPR wave function has a perfectly correlated position between the two particles, such that the x-coordinate of particle 2 is guaranteed to be the x-coordinate of particle 1 plus some constant offset x0. Oh, and just a comment on time evolution. So you might look at this constant offset x0 and say, well, wouldn't that grow over time? Well, yeah, but our wave function psi encodes the quantum state at the moment right before we do the measurement. And so to see how that works, let's go ahead and see what happens when we measure the momentum of particle 1. So what's going to happen is when we measure the momentum of particle 1, we're going to collapse our two-particle wave function, psi of x1 and x2, into two momentum eigenstates. Call it u sub p for the momentum eigenstate of particle 1, and psi sub p for the momentum eigenstate of particle 2. To see how this works, we can take our wave function, psi of x1, x2 is the integral over momentum of e to the I over h bar p x1 minus x2 plus x0, and we're just going to go ahead and rewrite that in a form where we pull apart that exponential into two exponentials. So then we have e to the negative I over h bar p x2 minus x0, and we're pulling out that e to the I over h bar p x1. The reason we want to write it in this form is because now psi of x1 and x2 appears as a sum over particle 1's momentum eigenstates, with expansion coefficients that are functions of particle 2's coordinates. This is a subtle point, so I want to linger here and just focus on this for a second. When our wave function is written in this form, and you have this integral over momentum space, you can think about that as a sum over all possible values of momentum. And what is it that we're summing over? Well, you have that green exponential, e to the I over h bar p x1, and that is a momentum eigenstate of particle 1. And you can see how when you sweep the momentum p from negative infinity all the way up to infinity, we're spanning the entire space of possibilities for momentum. By the way, you might say, hey, shouldn't we have some kind of envelope on this? Isn't it unrealistic to have p going all the way from negative infinity to infinity? And that's a great observation, but remember, this wave function is mathematically convenient. It is true that we could slap an envelope on it in momentum space and still make the same kind of arguments, but that goes without saying. So we're totally allowed to consider this mathematically elegant but somewhat unrealistic wave function because it's understood that it is substantially the same as a more realistic wave function as it pertains to the argument that we're going to be making, okay? All right, so then we have this sum over all the momentum eigenstates of particle 1, and we know that those eigenstates form a complete orthonormal basis, so it's mathematically guaranteed that we can write our wave function as this kind of an expansion. And then, by definition, this pink exponential, well, those are the expansion coefficients, right? Because they have to be. Because all we've done here for our wave function, we've just split out this exponential. We've just done an algebraic move. And so we can interpret, based on the structure of this equation, that if we were to expand our two-particle system in terms of momentum eigenstates of particle 1, then necessarily the expansion coefficients would have to be the expression given by this pink exponential. That's just a consequence of the structure of our particular wave function. Now, because we're dealing with a two-particle wave function, our expansion coefficients are not simple constants, but are actually themselves functions of particle 2's coordinate, as you can see. And the way to imagine that is if you pick any particular value for x2, then you see that psi of x1 for that value of x2 is simply an expansion over the momentum eigenstates of particle 1. But if you now imagine sweeping x2 back and forth, you can see how those expansion coefficients are going to change as a function of x2. So you see how the two-particle state has twice as many degrees of freedom as a one-particle state, which makes sense. Okay, so then here's where things get really interesting. If we measure the momentum of particle 1, we know from the rules of quantum physics that we would end up projecting psi onto a specific momentum eigenstate, which we can call u sub p of x1, which has a specific momentum p. Right? Because you know when you measure the momentum of a particle, you're collapsing its wave function onto a specific eigenstate. But then if we know that our wave function is the sum over momentum space, and we pick out a particular momentum, well, now that integral goes away because we've collapsed the wave function onto a very specific momentum eigenstate for particle 1. So you see the integral then goes away. And then psi, instead of being this expansion over all the possible momentum eigenstates of particle 1, is now just a particular momentum eigenstate of particle 1, times the expansion coefficient that goes with that particular momentum. So we simply have the integrand with a particular value of p. Now if you look at that expression, you can write this as psi sub p as a function of x2 times u sub p as a function of x1, where, as we talked about earlier, u sub p of x1 is a momentum eigenstate of the first particle, and it has an eigenvalue of p. That is to say, we now know that particle 1 has a momentum of p, and that's totally as expected. But now notice also that psi sub p of x2, which is e to the negative I h bar p x2 minus x naught, is also a momentum eigenstate, with eigenvalue of negative p for particle 2. And you can demonstrate that by applying the momentum operator to that exponential, and you end up seeing that a factor of negative p pops out, and that's your eigenvalue, and so therefore, particle 2 is in a momentum eigenstate with the momentum of negative p. So what have we shown here? Well, we've shown that with this specific two-particle wave function, psi of x1 and x2, if we measure the momentum of particle 1, then not only does particle 1 collapse into a momentum eigenstate, but so does particle 2. And in this case, the momenta of the particles are perfectly anti-correlated in that particle 1 has momentum p, and particle 2 has momentum of negative p, equal and opposite momentum. And that's a little weird, but it's not that weird. What gets weird is when next we're going to measure the position of particle 1, and then we're going to see that that ends up putting particle 2 into a position eigenstate. And then the question's going to be, well, wait a minute. If particle 1 and particle 2 are separated by an impassable barrier, then how can it be that we could measure the momentum or the position of particle 2 simply by a decision made at particle 1? Well, we'll get back to that argument in just a moment, but first I'd like to go through the math of measuring the position of particle 1 and showing how that collapses particle 2 into a position eigenstate. But before we can do that, we have to massage our equation for psi into another form by integrating over the momentum p. See, because if we put on our mathematician hats and we look at psi, we can say, oh, okay, we have an integral over momentum space of this expression, which is essentially e to the I p alpha, where alpha is going to be 1 over h bar x1 minus x2 plus x naught. But all of that, the x1, the x2, the x naught, the h bar, all of that is independent of momentum. And so when we think about how can we evaluate this integral, we may as well absorb all of those constants into some number alpha, which, because it doesn't depend on p, we may as well simply regard as constant for the purpose of evaluating this integral. Okay, but then the question becomes, how do we integrate over e to the I p alpha from p going from negative infinity all the way up to infinity? I mean, where do we even begin? Well, that's a tough question. But let's go ahead and take a look at what kind of a function we're dealing with in our integrand anyway. So here's a plot of e to the I p alpha. And it's like, whoa, that's a cool pattern. So e to the I anything is going to have a magnitude of 1, and it's only the complex phase that's going to change. And so in this plot, if you imagine that the opacity of the colors corresponds to the magnitude of the complex number, but because e to the I p alpha everywhere has a magnitude of 1, we have the same opacity all over the place. And then it's only the phase angle, which is encoded by this rainbow color map, that changes from one place to another. Now I know this pattern looks kind of dazzling, But if you just imagine a vertical line segment at some value of p, you can see there that that is simply a plane wave along the dimension of alpha. And so really all we have here is a whole bunch of different plane waves whose frequency in alpha changes as a function of p. And to integrate this over momentum space from negative infinity up to infinity, all we have to do is stack up all of these waves into a single function of alpha. Okay, but that's easier said than done, because how are we supposed to stack up all of these waves? What do we grab onto here? How do we even begin to parse this integral? This is actually quite a puzzle. And so to solve this, we have to think outside of the box. We have to be a little bit clever. So think about, what makes this integral difficult? Well, the infinities, for one thing, are kind of a thing. So we can lament the fact that our function still has a magnitude of 1 all the way out at infinity. And so we might think, oh, if only we could put a Gaussian envelope on this function and just make the infinities vanishingly small so we don't have to worry about them, then maybe we'd be able to integrate over a function like that. Because as p goes to negative infinity or infinity, the value of the function down there approaches 0, and so we don't even have to worry about it. And that's the right instinct to have, but the problem is, in life, you have to play the cards you've been dealt. And in math, you have to solve the integrals you've been dealt. And this function with the Gaussian envelope that so nicely makes the infinities go away is not the function that we actually have to deal with. However, is it not the case that our integral is the limit of this integral with the Gaussian envelope as the standard deviation of the Gaussian envelope approaches infinity? Or in other words, if we write our Gaussian as e to the negative epsilon p squared, where you see epsilon would be inversely proportional to the standard deviation, then isn't it the case that our wave function is the integral of this nice Gaussian enveloped function in the limit that this positive epsilon approaches 0? Well, yeah, that would appear to be the case, because as epsilon approaches 0, e to the negative epsilon p squared approaches 1, and then this Gaussian regulator that we're putting in our integral, that just goes away. So the way this trick works is that we're saying, we don't want to solve this integral because it's too complicated, but instead we'd rather solve this integral that does seem like we should be able to figure it out, and then, after integrating, we're going to take the limit so that the result of the integral converges onto our original integral. So it's kind of a neat trick, and so hopefully it works. All right, so then how do we evaluate the integral of negative epsilon p squared e to the I over h bar p alpha? And by the way, if you want to, you can absorb the 1 over h bar into the definition of alpha, or you can leave it as 1 over h bar. It doesn't matter either way. Okay, so having set up this integral, including our Gaussian envelope, next we're going to smush these two exponentials together and bring them into one exponential. So then our integrand becomes e to the negative epsilon p squared plus I over h bar p alpha. Okay, well, and so now we just have to integrate over some exponential function. Now, if you notice inside the exponential, we have a term which is quadratic in momentum, and we have a term which is linear in momentum. And that's a little tricky, but we can make it less tricky by completing the square. So if you complete the square, we see that the expression inside the exponential can be written as negative epsilon quantity p minus I alpha over 2 epsilon h bar squared minus alpha squared over 4 epsilon h bar squared. And that's just a bit of algebra when you think about how can we take our expression and write it in terms of momentum plus or minus something squared. And if you want to check that, you can evaluate the square and subtract the alpha squared term, and you'll see that these two expressions are in fact equivalent. But now, what's nice about this is we can go ahead and factor out that e to the negative alpha squared over 4 epsilon h bar squared. Go ahead and pull that outside of the integral, because relative to momentum, that's a constant that doesn't depend on momentum. And now then, what's left in our integral is e to the negative epsilon quantity p minus I alpha over 2 epsilon h bar squared. And that is an integral with a very nice form that we can go ahead and evaluate. Now, to evaluate this integral, let's go ahead and make the substitution. Q is defined as P minus I alpha over 2 epsilon h bar. So in other words, Q is just the momentum P with a constant offset. And so in that case, the differential element dq is equal to dp, and the limits of integration remain negative infinity and infinity, and so then we end up simply integrating over e to the negative epsilon q squared dq. Now this is a very famous integral. This is called the Gaussian integral, and it actually has its own Wikipedia page. And long story short, this integral has the solution of the square root of pi over epsilon. Now here, a very astute observer might say, hey, are we sure that the solution to this Gaussian integral is legitimate when q is not a real number, but is actually shifted by an imaginary constant in the complex plane? See, because in the definition of q, there's an I in the term that offsets q from p. And the short answer is, yeah, it's all good. Don't worry about it. There's a lot of details involved there with Cauchy's integral theorem and all that, so we're just going to gloss over that for now so as not to get stuck in the weeds. Okay, so then we end up with the very nice expression that our wave function is simply the limit as positive epsilon approaches 0 of the square root of pi over epsilon times e to the negative alpha squared over 4 epsilon h bar squared. So there's no more integral. Well, that's great. We're making a lot of progress. And now if we look at our expression, and you kind of blur your eyes a little bit and don't worry too much about the constants, you see, oh, that's a Gaussian. Because we have some constant times e to the negative alpha squared over some other constant, and that's a Gaussian. Now, it's not written in a form in which the standard deviation is manifestly evident, but with a bit of algebra, you can work it into that form if you want to. But then we think about it and it's like, we're taking the limit as epsilon approaches 0 of this Gaussian, where epsilon is in the denominator. So thinking about Gaussians, we can see that epsilon is going to be proportional to the standard deviation squared. So then it's like, whoa, oh, this is actually going to be a Dirac delta function. Because remember, the Dirac delta function, as a function of alpha, is defined as the limit of the standard deviation approaching 0 of the Gaussian function, which, when it's properly normalized, is 1 over the square root of 2 pi sigma exponential of negative alpha squared over 2 sigma squared. And if you compare that to our expression, you find that sigma corresponds to the square root of 2 epsilon h bar, and when you substitute that into the form of our Gaussian expression, you find that our wave function simply becomes 2 pi h bar times delta of alpha, because inside of that delta function is secretly the limit of the result of our integral. So that's all taken care of in the definition of the delta function. And so there it is. We find this very neat result that psi of x1 and x2 is 2 pi h bar times delta of alpha, where alpha is x1 minus x2 plus x naught. Now while we're here, whenever you have 2 pi h bar, we may as well write that as h. Because remember, the bar on the h bar is just shorthand for divide by 2 pi, so therefore 2 pi h bar is the same thing as Planck's constant h. And so our wave function becomes this very nice expression, h times delta of alpha. So let's write this out in terms of x1 and x2, just by unpacking alpha, and we find then a very neat and concise result, which is that our wave function of x1 and x2 is simply h times the Dirac delta function of x1 minus x2 plus x naught. So that's great. That's a very nice, convenient result. And you can see why Einstein, Podolsky, and Rosen chose this particular wave function to work with. It's a very clean wave function. But now I want to go ahead and mess it up just a little bit. Well, actually, we're not really messing it up. We're just going to modify it into a form that is going to segue nicely into our position measurement. So here, we're going to pull the move of reverse sifting property. I don't know if that's what it's actually called, but that's what I call it. So you see, we can write our wave function psi of x1 and x2 as the integral over x of h times delta of x minus x2 plus x naught times delta of x1 minus x. Now, I know this looks more complicated, and you might be wondering why we wrote the equation in this way. Well, the reason is that now we're writing psi as a sum over the position eigenstates of particle 1. So that's why we're writing it in this form, and we'll explore that in just a moment. But for now, before we move on, I just want to point out why this form of our wave function is equivalent to the form we just derived. And to see that, you just have to remember the sifting property. So if you look at the second Dirac delta function here, that is delta of x1 minus x, that is going to be 0 everywhere except when x equals x1. And so therefore, on the left delta function, delta of x minus x2 plus x naught, that's only relevant when x is x1. That is to say, when we have the delta function of x1 minus x2 plus x naught. Because for all other values of x, the delta function on the right is going to turn off the function. So you see here, this is just the sifting property, and we end up then, when we evaluate this integral, all the values of x are irrelevant, except for x equals x1, and if you evaluate that integral, you can show that indeed, it is equal to h times delta of x1 minus x2 plus x naught. So we haven't made any illegitimate moves, okay? We're allowed to write our wave function in this way. Okay, so now that we've done all that fancy integral math, I'd like to go ahead and collapse our wave function, psi of x1 and x2, into two position eigenstates, which we'll call v sub x of x1 and phi sub x of x2. So, we have seen that we can write our wave function psi of x1 and x2 as an integral over momentum, or equivalently, as an integral over position of this thing involving the product of these delta functions. And that is actually going to be a better form for figuring out what happens when we measure the position of particle 1. Because you'll notice that in this form, psi is actually being expressed as an integral over the position eigenstates of particle 1. Recall that v sub x of x1 equals delta of x1 minus x, where x is the position eigenvalue for some eigenstate v sub x. So remember, the delta function is a distribution which takes on a value of 0 everywhere except when its argument is 0. So delta of x1 minus x is going to be 0 everywhere except for where x1 equals x, because then x1 minus x is 0. And so therefore you can see why these are position eigenstates. V sub x of x1 is the state where particle 1 is completely localized onto some coordinate x. Well, then we can recognize in the integral shown above that this is already nicely expanded in terms of position eigenstates of particle 1, and so we can rewrite our expression as the integral over x of phi sub x of x2 times v sub x of x1 dx, where, as we know, v sub x of x1 are the position eigenstates of x1, and then we regard phi sub x of x2 simply as the expansion coefficients in that basis. But just like in the case of writing psi as an expansion over momentum eigenstates, where we saw that the expansion coefficients are going to be a function of x2, in this case, our expansion coefficients are still going to be a function of x2. But now they're going to be a different function of x2 because we're expressing psi as a sum over the position eigenstates of particle 1 rather than the momentum eigenstates. So then what kind of a function are we going to have for phi sub x of x2? Well, simply by inspecting the integral shown above, we can see that phi sub x of x2 is apparently going to be h times delta of x minus x2 plus x naught. But now if you look at that, you say, hey, that's a position eigenstate of particle 2, with a position eigenvalue of x plus x naught, because the function is entirely localized when x2 equals x plus x naught. So what that means is that if we measure the position of particle 1, then we collapse the wave function of particle 2 down into a position eigenstate. And we find also that the positions of the two particles are perfectly correlated, with x1 and x2 separated by a distance of x naught at the moment of measurement. So here's where things get weird. Depending on whether we measure the momentum or the position of particle 1, we can put particle 2 into a momentum or a position eigenstate. But nothing we do at particle 1 can affect particle 2 because the two are totally separated with an impassable barrier in between, not even in the same light cone. The only thing is they're in this entangled quantum state, whatever that means, as far as cause and effect. And yet, for some reason, the measurement decision that we make at particle 1 seems to be able to give us either the momentum or the position of particle 2. And then wouldn't that have to mean that particle 2 has both a real momentum and position? Right? Because otherwise, how do we have the choice to measure its momentum or its position, apparently without affecting it, unless it had both of those things to begin with? And then if it has those things to begin with, then wouldn't that mean that quantum mechanics is incomplete? Because quantum mechanics conventionally tells us that the position and momentum of a particle can't both be precisely known at the same time. And yet if they both exist, then that's kind of a shortcoming of quantum mechanics, right? And so that's the essence of the EPR paradox. Okay, well, hold on. What does this mean? What conclusions can be drawn from the fact that when we measure particle 1 in a momentum eigenstate, we put particle 2 into a momentum eigenstate? Or conversely, if we choose to measure the position of particle 1, we put particle 2 into a position eigenstate? That's super weird. But what does it mean? What are the logical implications of this realization? Well, in just a moment, we're going to get into part 2 of the paper, and we'll get into all the technical details. But I just want to say a few words about this from a common sense perspective. So it's like, okay, look, if you had one quantum particle and you thought about measuring its momentum or its position, and you think about the uncertainty principle, you realize the more precisely you measure momentum, the less you know about position, and vice versa. But if we're taking the assumption that quantum physics is complete, so that the uncertainty principle is not a flaw of quantum physics, but is actually reflecting the reality of momentum and position, then you might think that depending on whether we choose to measure momentum or position, we're sort of massaging the wave function in different ways. And so it's not too incredibly hard to believe that a measurement on a particle is going to affect its quantum state. Because you can just think, well, yeah, the measurement is going to massage the state into a certain state. But when you have an entangled state of two particles that are separated and there's an impassable barrier between them and they're not even in each other's light cones, now you run into a real problem when you think about if you're measuring particle 1, that really should have no effect whatsoever on particle 2. Unless you're assuming there's some kind of weird teleportation or spooky massaging at a distance or something, whatever we're doing on particle 1 should have no effect on the physical reality of particle 2, right? According to the principle of local realism. You can't just do something over here and have it affect something else way over there, unless there's a chain of cause and effect between here and there. And such chains of cause and effect can travel at most the speed of light. But then the problem is that we can measure the momentum of particle 2 or its position based purely on a measurement decision made at particle 1, which has no effect on particle 2. So how do you account for that? How can that be? Well, the obvious answer, and the answer that Einstein, Podolsky, and Rosen put forward is, look, this is clearly a sign that particle 2 has a physical momentum and position. Do you see it? Once you see it, you see it. This thing about the EPR paradox, it's all formal and fancy and really technical, but once you see it, it's like, oh, if we can measure the momentum or the position of particle 2 without touching particle 2, then clearly particle 2 inherently has that position and momentum information with it, and quantum physics just doesn't give us a complete description of the situation. So that's the obvious answer. Now, unfortunately, that's also the wrong answer. But it's wrong for a really trippy reason. Because the right answer is that in actuality, the collapse of the wave function is genuinely a non-local phenomenon. And so when we collapse our wave function psi by performing a measurement at particle 1, that measurement does update the quantum state at particle 2 instantaneously, faster than the speed of light, apparently without any concern for space itself, or whatever barrier happens to be between the two particles. This is what Einstein referred to as spooky action at a distance. And we'll talk a lot more about it in the upcoming video on Bell's theorem. Today I only bring up spooky action because I have to, because otherwise you would conclude what Einstein, Podolsky, and Rosen concluded, which is that quantum mechanics is incomplete. And it's like, well, we have every reason to conclude that. But reality is a little bit crazy, I'm sorry to say. But that's okay. I mean, we're thrown into this universe without any explanation, so what even is anything? I mean, Okay. Well, before I drift off into a rambling existential crisis, I think it's a good time for us to return to the paper and continue on with part 2, so we can hear, in their own words, Einstein, Podolsky, and Rosen describing the EPR paradox. So, if I've done a good job with the video so far, then what follows will at times feel a bit repetitive, because we're going to be encountering some of the same equations that we've already talked about. But if it feels a bit repetitive, that's actually a good thing, because that means we're in the right headspace to really contend with what Einstein, Podolsky, and Rosen are saying. So we have the imagery and the intuition in mind ready to go, and so now reading the actual text of the EPR paper is going to let us formalize and generalize these ideas. Okay, so part 1 of the EPR paper ended by saying that there's going to be a paradox in quantum physics. And then part 2 of the paper starts by setting up the thought experiment, which is going to show us that paradox. So, for this purpose, let us suppose that we have two systems, 1 and 2, which we permit to interact from the time t equals 0 to t equals t, after which time we suppose that there is no longer any interaction between the two parts. So this is the same thought experiment we were talking about earlier with particles 1 and 2. Though the way they phrase it here is actually even a bit more general than that, by saying two systems, 1 and 2. We suppose further that the states of the two systems before t equals 0 were known. We can then calculate with the help of Schrödinger's equation the state of the combined system 1 and 2 at any subsequent time, in particular for any t greater than t. That is to say, once the two particles separate out, we can use Schrödinger's equation to calculate the time evolution of this entangled quantum state. Let us designate the corresponding wave function by psi, and so that's the entangled wave function that can be calculated using Schrödinger's equation, given the fact that the initial state of the combined system is known. We cannot, however, calculate the state in which either one of the two systems is left after the interaction, because they're entangled. This, according to quantum mechanics, can be done only with the help of further measurements by a process known as the reduction of the wave packet. Nowadays, you often hear it called the collapse of the wave function. So the two particles remain in an entangled state until we measure one of them and collapse the wave function. Let us consider the essentials of this process. So first, the paper describes how we can expand psi over a set of eigenstates u sub n of x1, and then collapse it onto coefficients of that expansion, psi sub k, which is a function of x2. And remember, that's what we talked about earlier when we measured the momentum of particle 1. But now the paper is going to generalize that concept. So let a sub 1, a sub 2, a sub 3, be the eigenvalues of some physical quantity a pertaining to system 1, and let u sub 1 of x1, u sub 2 of x1, u sub 3 of x1, be the corresponding eigenfunctions, where x1 stands for the variables used to describe the first system, that is the coordinate of the first particle. Then our two-particle wave function psi, considered as a function of x1, can be expressed as psi of x1 and x2 is the sum over the eigenstates u sub n of x1, with some expansion coefficients that are only functions of x2, where x2 stands for the variables used to describe the second system, so the coordinate of the second particle, if we're thinking in terms of two particles. And here, psi sub n of x2 are to be regarded merely as the coefficients of the expansion of psi into a series of orthogonal functions u sub n of x1. Now this is a subtle and important point, so I want to linger on it for just a moment. Because u sub n are eigenfunctions corresponding to the observable A, we know that they comprise a complete orthonormal set, and so therefore we can expand psi as a sum over those eigenfunctions with some expansion coefficients. But if psi is a function of both x1 and x2, the expansion coefficients are going to depend on what value of x2 we put in our function. So for different values of x2, we find that this expansion over the eigenfunctions of x1 takes on different coefficients, and that's why the expansion coefficients are functions of x2. Now, why is it the case that the expansion coefficients are not functions of x1? Well, that's because the eigenfunctions of the physical quantity A for x1 comprise a complete orthonormal set. And so, relative to the degree of freedom of x1, those expansion coefficients are going to be constant. And then why is it that u sub n is only a function of x1 and not x2? Well, because by definition, u sub n are the eigenfunctions of x1 corresponding to the physical quantity A. And so that's why we have expansion coefficients that are functions of x2 and eigenfunctions that are functions of x1. So suppose now that the quantity A is measured, and it is found that it has the value A sub k. So out of all possibilities for the eigenvalue of A, we can have A sub 1, A sub 2, A sub 3, A sub k, We measure A, and we find the value A sub k. So for n equals k, that's the index of the eigenvalue that we find. It is then concluded that after the measurement, the first system is left in the state given by the wave function u sub k of x1, where the k index of the eigenfunction corresponds to the k index of the measured eigenvalue. And so therefore the second system is left in the state given by the wave function psi sub k of x2, where again the kth index corresponds to the fact that we measured the kth eigenvalue of A. This is the process of reduction of the wave packet. The wave packet given by the infinite series of equation 7 is reduced to a single term psi sub k of x2 times u sub k of x1 when we measure A and we find the eigenvalue A sub k. To illustrate this, you can imagine writing that sum of equation 7 in terms of each term just added up. So you just make the sum visible, where you can see the term for n equals 1, n equals 2, n equals k, And then when we measure the value of A, we find some eigenvalue A sub k. Therefore, particle 1 is in the eigenstate u sub k, and the wave function of particle 2 has to do with the expansion coefficients of that eigenstate u sub k in the original expansion of psi over all possible eigenstates u sub n. So the collapse of the wave function is quite literally a collapse of this infinite series down onto one particular term corresponding to the value of A that was actually measured. Okay, so now the paper goes on to make exactly the same point over again, but in a different way, simply using different letters, corresponding to a different physical quantity. So in the equations that we just looked at, the set of eigenfunctions u sub n of x1 is determined by the choice of the physical quantity A. If instead of this we had chosen another quantity, say B, having the eigenvalues b sub 1, b sub 2, b sub 3, and the eigenfunctions v sub 1 of x1, v sub 2 of x1, v sub 3 of x1, we should have obtained, instead of equation 7, where we expanded psi in terms of the eigenfunctions u sub n, and then collapsed that down with a measurement of the physical quantity A, instead of that, if we measure B, then we get the expansion of psi written as a sum over the eigenstates v sub s of x1, which correspond to the observable B. And then in this equation, we'll use phi sub s for the new coefficients. Now let me pause here and say, this equation is exactly the same thing that we just talked about. It's literally exactly the same concept, it's the same equation. We're just using different letters to say that now this is what the equation would be if we had measured the physical quantity B. But it's the same equation as if we would have measured the physical quantity A. Now, of course, the eigenfunctions are different, and likewise, the expansion coefficients are also going to be different. So equation 7 and equation 8 are different in that regard, but structurally, it's exactly the same concept. It's the concept that we can expand our two-particle wave function psi as a sum over eigenstates of particle 1. And then when we do that, we find that the expansion coefficients are functions of x2. If now the quantity B is measured and is found to have the eigenvalue B sub r, then we conclude that after the measurement, the first system is left in the state given by V sub r of x1, corresponding to the eigenvalue b sub r, and the second system is left in the state given by phi sub r of x2. Now this is exactly the same concept we just talked about, but now it's relative to the observable quantity b instead of a. But you see it's the same structure. So for equation 7, we expanded psi in terms of the eigenstates u sub n of x1, and then by measuring a and finding a sub k, we collapsed particle 1 into the eigenstate u sub k of x1, and 2 therefore became psi sub k of x2. Now then for equation 8, thinking in terms of the observable b, we first write psi as an expansion over the eigenfunctions v sub s of x1, corresponding to the observable b, and then we measure the quantity of b for particle 1, we find the eigenvalue b sub r, corresponding to the eigenfunction v sub r of x1, and therefore the wave function of particle 2 becomes phi sub r of x2. And if you see that, then you fundamentally see the EPR paradox. Because look what we have here. I mean, what is this? We have two wave functions assigned to the same reality? How can that be? That right there is the whole problem, right? So we see, therefore, that as a consequence of two different measurements performed upon the first system, the second system may be left in states with two different wave functions. On the other hand, since at the time of measurement, the two systems no longer interact, no real change can take place in the second system in consequence of anything that may be done in the first system. This is, of course, merely a statement of what is meant by the absence of an interaction between the two systems. Whether you want to imagine that as an impassable barrier, or the two particles being in different light cones, nothing we do at particle 1 should be able to affect particle 2. Thus, it is possible to assign two different wave functions, in our example psi sub k and phi sub r, to the same reality, that is, the second system after the interaction with the first. So how can you have two wave functions for the same reality? I mean, come on, what is this? This is absurd, right? This is like, clearly there's a problem with quantum physics here, you know? Now, from the modern point of view, we say, no, it's not a problem. Wave function collapse is non-local. There's not actually two different wave functions. When you measure the thing at particle 1, the wave function collapses at particle 2, so there is no paradox. Particle 2 has only one wave function, and so there's not actually a problem with quantum physics. Now that's the modern view, but the problem is it relies on the idea that wave function collapse is a non-local effect, which is philosophically intolerable, okay? It might be true, but it's intolerable. It's not good for your psychological well-being, but it does appear to be true. Well, anyway, Einstein, Podolsky, and Rosen then go on to give a specific example of a two-particle wave function in which the observable A is momentum and the observable B is position, and then they go on to show that you can put particle 2 into a momentum eigenstate or a position eigenstate simply by the choice of whether you measure the momentum or the position of particle 1. Now that math we've already gone through in detail, so here we can just breeze right through this section of the paper, just focusing on the words and the argumentation, having already seen the math, right? Okay. Now, it may happen that the two wave functions, psi sub k and phi sub r, are eigenfunctions of two non-commuting operators corresponding to some physical quantities p and q, respectively. That this may actually be the case can best be shown by an example, a very mathematically convenient example. Let us suppose that the two systems are two particles, and that psi of x1 and x2 is the integral over momentum of e to the I over h bar p x1 minus x2 plus x naught, where x naught is some constant. And that's the good old two-particle wave function that we know and love. All right, now let the physical quantity A be the momentum of the first particle. Then, as we have seen in equation 4, the definition of the momentum operator, its eigenfunctions will be of the form u sub p of x1 equals e to the I over h bar p x1, which is equation 10, corresponding to the eigenvalue p for the momentum. Since we have here the case of a continuous spectrum, meaning that momentum is not a discrete thing but it can take on a continuous value, then equation 7, where we expanded psi over the eigenfunctions u sub n of x1, will now be written as an integral rather than a discrete sum. So now we can write psi of x1 and x2 as the integral over the momentum of the momentum eigenfunctions u sub p of x1, each one multiplied by its expansion coefficients psi sub p of x2, where psi sub p of x2 is evidently e to the negative I over h bar p x2 minus x naught. And you can show that by simply looking at the definition of our wave function psi, and remember earlier we split out the exponential into two exponentials, and so this result about psi sub p follows directly from the definition of psi. This psi sub p, however, is the eigenfunction of the operator p hat equals negative IH bar partial x2, corresponding to the eigenvalue negative p of the momentum of the second particle. And that is to say that for this wave function psi, the momenta of the two particles are going to always be equal and opposite, that is, perfectly anti-correlated, and that when we measure the momentum of particle 1, we put both particle 1 and particle 2 into a momentum eigenstate, as we talked about before. Okay, so then the paper goes on to consider position. On the other hand, if B is the coordinate of the first particle, that is the position, then it has, for eigenfunctions, v sub x of x1 equals delta of x1 minus x, corresponding to the eigenvalue x, where delta of x1 minus x is the well-known Dirac delta function. Now then in this case, equation 8, which is where we expanded psi in terms of the eigenfunctions v sub s of x1 corresponding to the physical quantity b of particle 1, now becomes a continuous integral over the position eigenstates of particle 1, where the expansion coefficients phi sub x of x2 by inspection are going to equal h times delta of x minus x2 plus x naught, for reasons that we already calculated when we did the integrals and the reverse sifting property and all of that. Now in the paper, between equation 15 and equation 16, you see there's a lot of math implied, and so that's why I wanted to go ahead and look into all this math before we started reading part 2, so that here we can just breeze right through it without getting hung up on the equations, so that way we didn't have to go on a long mathematical detour right now. Because I want to stay focused in the argument itself and in the words and in the philosophy now. Okay, so this phi sub x, however, is the eigenfunction of the operator q hat equals x2, that is the position of the second particle, corresponding to the eigenvalue x plus x naught of the coordinate of the second particle. And so we find that when we measure the position of particle 1, we put both particles into position eigenstates. Now since momentum and position do not commute, that is, p hat q hat minus q hat p hat equals h bar over I, also known as negative IH bar, then we have shown that it is, in general, possible for psi sub k and phi sub r to be eigenfunctions of two non-commuting operators, corresponding to physical quantities. So now you see how this argument with the specific wave function psi provides a specific example in the context of a more general argument about how our choice of what to measure at particle 1 can influence the quantum state of particle 2, and that apparent weirdness about the two wave functions can even apply when you're talking about two eigenstates of non-commuting operators, which is really an extreme case because it shows you that you can have two wave functions for particle 2 corresponding to observable quantities that apparently shouldn't have simultaneous reality, according to the standard view of quantum physics. And so you see how we've constructed this very confusing situation. Well, what are we to make of this? All right, zooming out of our specific example with our specific psi, and returning now to the general case contemplated in equations 7 and 8, that is, where we expanded our two-particle wave function psi over eigenstates of particle 1, and then in the first case collapsed particle 1 onto u sub k of x1, and in the second case measured quantity b and collapsed particle 1 onto the eigenstate v sub r of x1, and in so doing we saw that we can describe particle 2 with two different wave functions. Then we assume that psi sub k and phi sub r are indeed eigenfunctions of some non-commuting operators p hat and q hat, corresponding to eigenvalues p sub k and q sub r, respectively. Thus, by measuring either a or b, we are in a position to predict with certainty, because these are eigenfunctions, and without in any way disturbing the second system, either the value of the quantity p, that is p sub k, or the value of the quantity q, that is q sub r. In accordance with our criterion of reality, in which if you can predict something with certainty without disturbing the system, then that thing is real. In the first case, equation 7, we must consider the quantity p as being an element of reality, and in the second case, equation 8, the quantity q is an element of reality. But as we have seen, both wave functions psi sub k and phi sub r belong to the same reality. So it would appear then that p and q are simultaneously real, which is not supposed to be a thing, according to the official story of quantum mechanics. So what's going on here? What is this? What do we make of this? Well, previously we proved that either 1, the quantum mechanical description of reality given by the wave function is not complete, or 2, when the operators corresponding to two physical quantities do not commute, the two quantities cannot have simultaneous reality. Starting then with the assumption that the wave function does give a complete description of the physical reality, that is the negation of 1, we arrived at the conclusion that two physical quantities with non-commuting operators can have simultaneous reality, which is the negation of 2. Thus, the negation of 1 leads to the negation of the only other alternative 2. And that's a paradox, because it contradicts our disjunctive syllogism. We are thus forced to conclude, we have no choice, that the quantum mechanical description of reality given by wave functions is not complete, because the negation of 1 leads to a paradox, and therefore 1 must be true. So that's the argument. The paper ends with a very interesting comment on local causality and an allusion to hidden variables. One could object to this conclusion on the grounds that our criterion of reality is not sufficiently restrictive. Indeed, one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous elements of reality only when they can be simultaneously measured or predicted. So what they're saying here is that even though we showed that we can measure the momentum or the position of particle 2 based on a decision made at particle 1, at the same time we only get to choose one of those options. You see, so it's not the case that we can with certainty predict simultaneously the momentum and the position of particle 2. Even with our wave function collapse, we're still not able to do that, because we have to make a measurement choice at particle 1. Do we want momentum, or do we want position? And this inference about the position and the momentum of particle 2 being simultaneously real depends on the fact that we don't have any cause and effect going from particle 1 to particle 2. So you see how local causality is such a critical assumption of this argument. But now let's play the devil's advocate and let's say wave function collapse is non-local, it is simultaneous, and so when we measure the momentum of particle 1, we're massaging the wave functions of particle 1 and particle 2 simultaneously into a momentum eigenstate, and even though that's non-local, that's fine, quantum physics allows it for whatever reason, and so because our measurement choice at particle 1 is able to massage the state at particle 2, then that doesn't mean that particle 2 has a real position and has a real momentum. It just means we could have massaged particle 2 into a momentum eigenstate or into a position eigenstate. And so therefore, this thing about separating particles and putting an impassable barrier between them really doesn't matter if we allow for the possibility that wave function collapse can be a non-local phenomenon. On this point of view, since either one or the other, but not both simultaneously, of the quantities p and q can be predicted, they are not simultaneously real. But this makes the reality of p and q depend on the process of measurement carried out on the first system, which does not disturb the second in any way, which would violate local causality. You're saying you do something at particle 1 and that somehow massages the wave function at particle 2. Well, no, no reasonable definition of reality could be expected to permit this. Now, this is where John Stuart Bell is going to come in and say, well, how about an unreasonable definition of reality? We'll get to that in a future video. Well, anyway, the paper concludes with an allusion to hidden variables. While we have just shown that the wave function does not provide a complete description of the physical reality, we left open the question of whether or not such a description exists. Could a complete theory exist? Hey, maybe, right? Who knows? We believe, however, that such a theory is possible. But what does it mean for such a theory to be possible? Well, that means that there must be some kind of hidden variables that quantum mechanics doesn't yet account for. That is, there must be some elements of reality that are not, as of yet, elements of the conceptual machinery of quantum mechanics. So by hidden variables, just think of that as blind spots in quantum mechanics. Ingredients that we haven't yet added into the theory in order to have a complete accounting of physical reality. Now, as we'll see in the video on Bell's theorem, this idea about hidden variables is actually not correct. In reality, the EPR paradox is resolved by non-local wavefunction collapse. Now, I should say, just so no one leaves me a comment about this, there are theories which attempt to reconcile locality and the EPR paradox and hidden variables by casting all of these equations in the context of a superdeterministic metaphysics. And you can read about superdeterminism if you want to. It's generally considered to be absurd. And I know some people might get upset at me saying that. But no, I will happily debate anyone on this topic. Superdeterminism is philosophically a non-starter. But that's a story for another day. All right, well, that's the paper. I hope you got something out of this. I hope you had a good time. And I hope this has given you something to think about. Like I mentioned earlier, I am going to do a follow-up video on Bell's theorem. And so that'll be a lot of fun. Stay tuned for that. Kind of an existentially challenging video, but it's something we have to talk about, right? So yeah, I'll see you later. Thanks for watching. I want to say thank you to all of you who are supporting the channel on Patreon. Your support really means a lot. I don't do ad reads on my videos. I'm not trying to sell you some VPN or some supplements or whatever. No, I just want to talk about science. And thanks to your support, I'm able to put in the time and effort in these videos, and it's a practical endeavor. It really makes sense for me to do this. And so I just want to let you know, I'm so grateful for all of you for giving me that opportunity. It actually reminded me, a few years ago I was scuba diving, and at the end of the dive, the instructor said, hey, thank you all for coming out here. If not for you, I'd have to get a real job with real shoes. And so as I'm sitting here barefoot recording this, I'm reminded of the scuba instructor's gratitude, and I just wanted to reflect that same sentiment, because I truly am grateful for this wonderful opportunity, so thank you all.